Every object you've ever seen in the night sky has one thing in common. It belongs here. The planets, the comets, the asteroids, all born from the same ancient disk of gas and dust that formed our sun. But in 2025, astronomers detected something different, something that didn't belong to our solar system at all. It was moving too fast, its path was wrong, and gravity could not hold it. This was not a returning comet. This was not a wandering asteroid. It was a visitor, an object that had spent billions of years traveling between the stars before briefly crossing our cosmic neighborhood. Scientists named it 3I Ibi Atlas, only the third confirmed interstellar object ever discovered, and unlike the others, this one arrived with a visible coma, a glowing signature that allowed astronomers to study material from another star system in unprecedented detail. For a short time, the solar system was no longer closed. Something from the outside had entered. For most of human history, the night sky felt familiar. The stars stayed fixed, the planets followed predictable paths, and comets, no matter how dramatic they appeared, always belonged to the same cosmic family, our solar system. Everything above us seemed connected to the sun, until that assumption quietly broke. In July 2025, a telescope system built to protect Earth noticed something unusual. Not bright, not threatening, just different. The object's motion didn't match anything astronomers expected. It wasn't slowing down. It wasn't curving back toward the sun. It wasn't following a long, looping orbit like distant comets usually do. Instead, it was doing something rare. It was passing through, and then leaving forever. That single detail, its trajectory, immediately raised alarms across the astronomical community, because objects that belong to the solar system don't behave like that. A path that didn't belong. Every object bound to the sun follows the same rule. Gravity eventually pulls it back. Even the most distant comets from the Oort cloud, drifting for millions of years, are still tied to the sun's influence. But this object wasn't. Its orbit was hyperbolic, a mathematical curve that means one thing very clearly: the sun could not capture it. This object had too much speed, too much energy. It was not a returning visitor. It was a passing traveler. Astronomers quickly realized what that meant. This object did not form here. It did not share the solar system's origin story. It came from interstellar space, the vast region between stars. They named it 3I-ATLS. The 3I designation mattered more than it seemed. It stood for Third Interstellar Object. Only two had ever been confirmed before, and none had been observed quite like this. A visitor older than Earth. To understand the importance of 3I-ATLS, you have to think far beyond human time. Long before Earth existed, before the sun ignited, before our planets formed, other stars were being born. Around those stars, planets collided, migrated, and settled into chaotic early systems. And during that violent process, countless objects were flung outward, ejected completely from their home systems. 3I-ATLS was likely one of them. At some point in the distant past, gravity from massive planets launched this object into deep space. No star to orbit, no warmth, no light. For millions, possibly billions of years, it drifted silently through the Milky Way, frozen, unchanged, preserved, until it crossed paths with our sun. Detection was a matter of timing. What makes 3I-ATLS extraordinary is not just what it is, but that we found it at all. Interstellar objects are difficult to detect because they are small, fast, and unpredictable. They don't follow known paths. They don't announce their arrival. They appear suddenly and vanish forever.
The ATLAS telescope system, designed to scan the sky for near-Earth hazards, just happened to be looking in the right place at the right time. Without it, 3I ATLS would have passed unnoticed. Another cosmic message missed. Speed told the story. As astronomers refined their measurements, the evidence became undeniable. 3I ATLS was traveling at more than 200,000 kilometers per hour relative to the Sun. That speed could not be explained by a solar system origin. It had to come from somewhere else. Speed in space is history. It tells you how far something has traveled and how violently it was launched. And 3I ATLS told a clear story. This object was not born here. When the comet woke up, as 3I ATLS moved closer to the Sun, something remarkable happened. It began to glow. Ice that had remained frozen for eons finally felt warmth. Not heat, just enough energy to change state. Solid ice turned directly into gas, a process called sublimation. A bright coma formed around the nucleus. Dust streamed outward, creating a visible tail. This behavior confirmed something crucial. 3I ATLS was a true comet, natural, physical, predictable. Not artificial, not technological, not mysterious in its behavior. It followed the same physical laws as comets from our own solar system, just with a very different origin. Why that matters? There was intense interest after the first interstellar object, Oumuamua, because it didn't behave like a typical comet. 3I ATLS removed that uncertainty. It behaved exactly as physics predicted. And that made it far more valuable, because now scientists could study ice chemistry from another star system, dust shaped by a different sun, organic molecules formed elsewhere in the galaxy, all without sending a spacecraft. A cosmic sample delivered to us. Normally, studying another star system requires advanced missions, decades of travel, and enormous budgets. 3I ATLS delivered itself, a natural sample of alien planetary material passing directly through our neighborhood, and it would never return. That urgency triggered rapid global observations. Telescopes on Earth and in space turned toward it. Every photon mattered, because once it left, it was gone forever. What 3I ATLS really tells us. This comet was never a threat. It didn't endanger Earth. It didn't alter orbits. It didn't carry life. What it carried was perspective. It proved that the solar system is not sealed, that material moves freely between stars, that planets exchange debris, that the Milky Way is not a collection of isolated systems, but a connected, dynamic environment. 3I ATLS was not special because it was strange. It was special because it was ordinary, just not from here. And once you accept that objects from other star systems can pass through ours, a bigger question emerges. What else is quietly moving between the stars, waiting to be discovered?
How scientists detected, tracked, and studied 3I-ATLS. Detecting something from another solar system is not like spotting a planet or a bright comet. There is no schedule, no prediction, no warning. Interstellar objects don't announce themselves. They appear suddenly, already moving too fast to follow for long. The telescope that found a stranger. 3I-ATLS was discovered by a system designed for an entirely different purpose. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, exists to scan the sky for objects that might threaten Earth. Every clear night, its telescopes sweep wide regions of space, looking for anything that moves. Most of what they detect are familiar objects, asteroids with known orbits, comets already cataloged. But this object didn't match anything.
When Atlas first recorded it, it looked unremarkable, a faint point of light, barely distinguishable from background stars. What made it stand out was its motion. Frame by frame, it was moving too fast and in the wrong direction. Orbit calculations changed everything. Astronomers immediately began calculating its orbit. This is where interstellar objects reveal themselves. Orbit calculations are unforgiving. They don't care about theories or excitement. They only follow gravity. As more observations came in, the numbers converged on one conclusion. The orbit was hyperbolic. Not elliptical, not parabolic. Hyperbolic means escape. It meant the sun's gravity was not strong enough to pull the object into orbit. This was not a returning comet. This was a visitor on a one-way path. Within days, the announcement went out. Astronomers around the world understood what they were seeing. Only the third confirmed interstellar object ever detected. And, unlike the first two, this one was active, brightening, revealing itself. A global response began. Once the interstellar nature of 3I-ATLS was confirmed, time became critical. Objects like this move quickly. Every day matters. Every observation window is precious. Telescopes across the globe were redirected, from Chile to Hawaii, from Europe to Asia. Space-based observatories joined in as well. NASA, ESA, and other agencies coordinated schedules to capture as much data as possible. This wasn't just another comet. This was foreign material, and it wouldn't be here long. Watching a comet wake up. As 3I-ATLS approached the Sun, scientists watched closely. Interstellar objects have never experienced our Sun's warmth before. This was the first time sunlight was interacting with its surface. At a certain distance, the transformation began. Frozen gases trapped inside the nucleus started to sublimate. A coma appeared, then a tail. This confirmed something crucial. 3I-ATLS was not inert rock. It was a volatile-rich comet, similar in structure to comets formed around our own solar system. This was important because it meant scientists could use the same physical models they use for solar system comets. The laws of physics still applied, even across star systems. Spacecraft joined the observation. Several space missions played a role in observing 3I-ATLS. While none were designed specifically for it, their instruments proved invaluable. Solar observatories captured images as the comet passed closer to the Sun. Other spacecraft tracked its position and brightness, helping refine models of its size, speed, and activity. For the first time, astronomers were observing an interstellar comet not just as a moving point, but as a dynamic, evolving object. Jets formed, brightness changed, gas and dust interacted with solar radiation. This was not theory. This was real-time science. Why speed made observation difficult. 3I-ATLS was moving far faster than typical comets. That speed created challenges. Long exposure images could blur. Tracking required constant adjustment. Small timing errors could lose the object entirely. Interstellar objects don't give second chances. If you miss them, they are gone forever. This forced astronomers to work faster than usual. Data was shared openly and rapidly. Observations were uploaded, analyzed, and compared, sometimes within hours. Modern astronomy at full speed. Determining size and structure. One of the hardest things to measure was the size of the comet's nucleus. The coma hides the solid core. But by studying brightness changes and gas output, scientists estimated the nucleus to be only a few kilometers wide. Small, but significant. Its rotation was also studied. Brightness fluctuations suggested the nucleus was spinning, but not smoothly. They were hints of wobble. irregularity, clues that its internal structure may not be uniform. A comet with a memory. One of the most fascinating aspects of 3I-ATLS was what it didn't show. There were no signs of repeated heating cycles, no evidence of surface erosion from previous close passes to a star. That suggested something remarkable. This may have been the first time 3I-ATLS ever passed this close to any star. For billions of years, it remained frozen, preserved, a time capsule from another solar system. A race against time. As weeks passed, the comet began its exit. Its brightness faded, its coma thinned. Instruments gathered the last usable data. Astronomers knew this was the end of the encounter. No follow-up mission, no second flyby. 3I-ATLS was already accelerating away, heading back into interstellar space. But what it left behind was extraordinary. Terabytes of data, spectra, images, motion profiles, enough information to study for years. Why this detection matters. Before 2017, interstellar objects were theoretical. Now they're confirmed, and with 3I-ATLS, they're observable in detail. This detection proved that interstellar visitors are not rare anomalies. They are part of the galaxy's natural circulation. Material moves between stars, planetary systems exchange debris, and future telescopes, like the Vera C. Rubin Observatory, are expected to find many more, dozens, perhaps hundreds. 3I-ATLS wasn't just discovered, it marked the beginning of a new field of astronomy, one where the solar system is no longer isolated. And that sets the stage for the next question. Now that we know how it was detected, what exactly is it made of?
What 3I-Atlas is made of? Chemistry from another star system. Once astronomers confirmed that 3I-Atlas was truly interstellar, the most important question became simple. What is it made of? Because composition tells a story that motion alone cannot. It reveals where an object formed, what conditions shaped it, and how different or similar other star systems might be to our own. Reading light like a fingerprint. Scientists don't touch comets. They read them. When sunlight hits a comet's coma, atoms and molecules absorb and emit light at very specific wavelengths. This creates a spectrum, a chemical fingerprint. And 3I-Atlas offered a rare opportunity. Unlike Oumuamua, which remained faint and inactive, 3I-Atlas was alive, outgassing, glowing, revealing itself. The early molecules detected. Early spectroscopic observations quickly identified familiar compounds: water vapor, carbon monoxide, carbon dioxide. These are common in solar system comets, and that discovery alone was significant because it suggested that the basic ingredients of comet formation are not unique to our Sun. They appear to be universal. But there was more. As the comet brightened, astronomers detected cyanide compounds and complex carbon-based molecules. These are not signs of life, but they are the raw materials from which chemistry and eventually biology can emerge. The green glow that caught attention. One of the most visually striking features of 3I-Atlas was its color. As it approached the Sun, the coma developed a noticeable green glow. This wasn't artistic lighting, it was physics. The color came from diatomic carbon, pairs of carbon atoms excited by sunlight. When these molecules relax, they emit green light. This phenomenon is seen in some comets, but rarely so clearly. The presence of diatomic carbon told scientists several things at once. First, it confirmed that 3I-Atlas contains carbon-rich material. Second, it suggested that its ices formed in a cold, carbon-friendly environment. And third, it showed that despite its alien origin, the comet responded to sunlight in familiar ways.
similar, but not identical. As more data came in, a subtle pattern emerged. 3I-Atlas looked like a comet, behaved like a comet, but it wasn't an exact match to those from our solar system. The ratios of gases were slightly different. The balance between water, carbon monoxide, and carbon dioxide suggested it may have formed farther from its parent star than many solar system comets, possibly in a colder region, possibly around a star with a different chemical history than our Sun. This is where interstellar comets become powerful tools. They don't just tell us what comets are, they tell us how planetary systems vary. A time capsule from elsewhere. One of the most remarkable aspects of 3I-Atlas is how little it appears to have changed. Solar system comets make repeated passes near the Sun. Each pass strips material away. Each pass reshapes the surface. 3I-Atlas likely never experienced stellar heating before. For billions of years, it drifted frozen between stars. No warming, no erosion, preserved. That makes its chemistry especially valuable. It's not a recycled object, it's a pristine sample from another planetary system. Organic molecules, not life, but potential. It's important to be precise. 3I-Atlas did not show signs of life. No biology, no cells, no organisms, but it did carry organic molecules, carbon-based compounds that form naturally in space. These molecules are common in star-forming regions and young planetary disks. This supports a growing idea in astronomy. The building blocks of life may be widespread throughout the galaxy. Not life itself, but the chemistry that makes life possible. Comets like 3I-Atlas act as delivery systems. They move material from one star system to another. And while the odds of life transfer are extremely low, the transfer of chemistry is not. Jets, heat, and hidden layers. As the comet continued to warm, astronomers noticed something else. The release of gas was not uniform. Jets erupted from specific regions. Some areas were active, others were quiet. This uneven activity suggested a layered internal structure. Different ices trapped at different depths, different compositions exposed at different times. This internal complexity hinted that 3I-Atlas formed in a dynamic environment, not a quiet disk, but a turbulent one. Why composition changes everything. Before interstellar comets were observed, astronomers had to rely on theory, models of planet formation, simulations, comparisons between solar systems. 3I-Atlas changed that. It provided direct evidence. Material formed around another star can be sampled without leaving Earth. And what it revealed was both comforting and humbling. Comforting because the chemistry looked familiar, humbling because it showed how much more there is to learn. A universe that reuses its ingredients. 3I-Atlas suggests that the universe builds planets using a shared toolkit: ice, dust, carbon, energy. The details vary, the outcomes differ, but the fundamental process appears consistent. This realization reshapes our understanding of how common planetary systems might be, and how common the ingredients of life could be. 3I-Atlas didn't answer whether life exists elsewhere, but it strengthened the case that the conditions for life are not unique to Earth. And that brings us to the next chapter. Now that we understand what this interstellar visitor is made of, what happened when it passed closest to Earth, and how did the world react to watching something from another star cross our skies?
Closest approach, when Earth watched a visitor from another star. By the time 3I-Atlas reached the inner solar system, astronomers had already confirmed its identity. This was no longer a mystery object. It was an interstellar comet, a traveler that had crossed unimaginable distances before briefly passing through our cosmic neighborhood. And now, It was approaching its closest point to Earth. How close is close in space? In December 2025, 3I Atlas made its closest approach to our planet. At its nearest point, the comet passed roughly 270 million kilometers away. To put that into perspective, that's almost twice the distance between Earth and the Sun. In everyday terms, that sounds enormous. In astronomy, it's close enough to study in detail. There was never any danger, no collision risk, no gravitational disturbance, no threat to Earth's orbit, but the proximity offered something rare, a clear window to observe an object that did not originate here. A global observation campaign. As the date approached, observatories around the world prepared. Professional telescopes scheduled observation blocks, amateur astronomers dusted off equipment, astronomy clubs planned public viewing sessions. For scientists, this was a race against time. Interstellar objects don't linger. Every day after closest approach, 3I Atlas would fade. Its brightness would drop, its coma would thin, and then it would be gone forever. Visibility from Earth. At peak brightness, 3I Atlas was visible through small telescopes and high-quality binoculars. It wasn't a naked-eye comet, but for those who knew where to look, it appeared as a faint, glowing smudge, moving slowly against the stars. For many observers, this moment carried a strange weight. They weren't just looking at a comet, they were looking at material from another star system, light reflected off ice and dust that formed around a different sun long before Earth existed. The human perspective. Astronomy often deals with abstractions, numbers, spectra, models, but moments like this make it tangible. For a brief time, people on Earth shared the sky with something truly foreign. Social media filled with images, not spectacular, but meaningful. Small telescopes capturing a faint glow with captions that read, "Not from here." It was a reminder that Earth is not isolated, that the solar system is not closed, that the galaxy is alive with motion. Scientific gold during the flyby. For scientists, the closest approach was more than symbolic. It was a data goldmine. Spectroscopic measurements were refined, brightness variations were tracked hour by hour. Jets and outgassing patterns were monitored in detail. The changing geometry between Earth, the comet, and the Sun allowed astronomers to observe how sunlight interacted with the coma from different angles. This helped refine models of gas release rates, dust particle sizes, and surface activity patterns. A comet reveals its rotation. During the flyby, subtle fluctuations in brightness became easier to detect. These fluctuations revealed something important. 3I Atlas was rotating, and not smoothly. The light curves suggested a complex spin, possibly tumbling or wobbling slightly. This irregular rotation hinted at an uneven interior, different densities, different layers, evidence of a violent formation history. A first and last encounter. One of the most sobering aspects of the flyby was knowing it would never happen again. 3I Atlas was not bound to the Sun. Once it passed, gravity would sling it outward, back into interstellar space. There would be no return, no second pass, no chance for a spacecraft rendezvous. This was it. That knowledge added urgency to every observation. Every photon captured was irreplaceable. The public reaction. While this event didn't dominate headlines, it captured the imagination of those who understood its significance. Science enthusiasts, astronomers, educators. The idea that something from another star system could drift through ours felt both unsettling and inspiring, not because it was dangerous, but because it made the universe feel closer, more connected. Leaving Earth behind. After closest approach, 3I Atlas began to fade. Its tail shortened, its coma weakened. It accelerated outward, moving away from the Sun and away from Earth. By early 2026, only large telescopes could still detect it. Soon after, it disappeared from view entirely. But the encounter was not over. The data collected during those weeks would be studied for years, reanalyzed, compared, debated.
What this flyby changed. Before 2017, interstellar objects were theoretical. By 2025, they were observable. By 3i Atlas, they were understood. This flyby proved that humanity can detect, track, and study visitors from other star systems in real time, and that future discoveries will not be rare flukes, but part of a growing field. 3i Atlas came close enough to be seen, close enough to be studied, close enough to remind us how vast the universe truly is, and as it vanished into the dark, it left behind a final question. Now that we've seen one so clearly, what will the next interstellar visitor show us?
Strange jets, silent lessons, and what 3i-Atlas changed forever. As 3i-Atlas began its slow departure from the inner solar system, astronomers noticed something unexpected. The comet wasn't just fading, it was changing. And those changes revealed some of the most important clues about its true nature. Jets that didn't behave normally. Most comets release gas and dust in a relatively predictable way. As sunlight warms the surface, ice sublimates evenly, producing smooth, symmetrical jets. 3i-Atlas did not follow that pattern. Instead, astronomers observed jets erupting from specific regions of the nucleus. Some turned on suddenly, others faded just as quickly. The outgassing appeared uneven and unstable. This behavior immediately caught scientists' attention. A rotating, possibly tumbling core. By carefully tracking brightness variations, researchers reconstructed how the comet was spinning. The result was surprising. 3i-Atlas was rotating, but not smoothly. It appeared to wobble, possibly tumble. This suggested the nucleus was not a solid, uniform body. Instead, it was likely a loosely bound collection of ice and rock, a structure shaped by violent formation processes in its original star system. In other words, 3i-Atlas carried the scars of a chaotic past. First-time heating after billions of years. One of the most important conclusions from studying the jets was this: 3i-Atlas was likely experiencing its first close encounter with any star. Solar system comets often show signs of repeated heating, layered crusts, exhausted volatile regions, surface erosion. 3i-Atlas showed none of that. Its activity appeared fresh, raw, unprocessed. That means the comet's interior had remained frozen and unchanged for billions of years. It was not just interstellar, it was pristine. Why that matters to science. This made 3i-Atlas incredibly valuable. It wasn't a recycled object. It wasn't altered by multiple stellar passes. It was a time capsule from another planetary system. Studying its behavior allowed scientists to test theories of comet formation outside our own solar system, and the results were revealing. Different star, familiar physics. Despite its alien origin, 3i-Atlas followed the same physical laws as solar system comets. Ice sublimated at expected temperatures, gas expanded as predicted, dust behaved according to known models. This was a powerful result. It suggested that while star systems differ, the rules of planet formation are universal. Different environments, same physics. What it didn't show was just as important. Equally important were the things 3i-Atlas did not show. There was no evidence of artificial propulsion, unnatural acceleration, metallic surfaces, or engine-like behavior. Despite speculation in public forums, every piece of data pointed to a simple conclusion. 3i-Atlas was natural, alien in origin, but not alien in design. This reinforced a crucial principle of science. Extraordinary claims require extraordinary evidence, and 3i-Atlas did not provide that evidence. It provided something better: understanding. A lesson in scientific restraint. The quiet achievement of the 3i-Atlas discovery was how the scientific community responded. There was excitement,
But there was also caution. Rather than jumping to conclusions, researchers focused on data, on measurements, on repeatable observations. In doing so, they showed how science advances, not through speculation, but through patience. The bigger picture, a galaxy in motion. Perhaps the most profound lesson of 3I-Atlas is what it implies about the Milky Way. Our galaxy is not static, it is not orderly, it is constantly exchanging material. Objects are ejected from star systems, they wander for eons, and occasionally they pass through others. This means planetary systems are not isolated islands. They are part of a galactic ecosystem. Implications for the search for life. While 3I-Atlas did not show life, it strengthened a growing idea. The ingredients of life are widespread. Organic molecules form naturally, they travel, they mix. This doesn't mean life is common, but it does mean life's raw materials are not rare. Comets like 3I-Atlas may play a role in spreading chemistry across the galaxy, not intentionally, not dramatically, but steadily. The end of the encounter. As months passed, 3I-Atlas faded beyond detection. Its coma vanished, its jets shut down. Gravity carried it outward, back into the dark between stars. It will never return. It will never orbit the sun again. Earth will never see it twice. But its impact on astronomy remains. What 3I-Atlas changed forever. Before 2017, interstellar objects were theoretical. Before 2019, they were rare curiosities. After 3I-Atlas, they became scientific tools. Astronomers now know interstellar comets are detectable. Their chemistry can be measured. Their behavior can be modeled. Their origins can be studied. Future observatories will find more, many more. And when they do, 3I-Atlas will be remembered as the moment interstellar astronomy came of age. Final reflection. 3I-Atlas was not a messenger with answers. It was a messenger with context. It reminded us that Earth is part of something vast, that our solar system is open to the galaxy, and that even the smallest, faintest object can reshape how we see the universe. A piece of ice and dust from another star crossed our path and quietly changed astronomy forever.
A visitor that changed how we see the universe. In the end, Comet 3I-ATLS did not bring danger. It did not bring answers about alien life, and it did not change Earth's fate. What it brought was something quieter and far more powerful: perspective. For billions of years, this small body of ice and dust drifted between the stars. No destination, no audience, no purpose beyond motion itself. It existed long before Earth formed, long before the sun ignited, long before humanity ever looked up and wondered. And then, by pure chance, it crossed our path. For a brief moment in cosmic time, two star systems touched, not with planets, not with life, but with material, with chemistry, with shared physics. 3I-ATLS reminded us that the solar system is not a sealed room, it is a doorway. Matter enters, matter leaves. The Milky Way is not a collection of isolated worlds, it is a connected system, constantly exchanging pieces of itself. This comet did not speak, it did not signal, it did not announce intention. Yet its silence said something profound, that the universe is older, larger, and more interconnected than we instinctively imagine. When astronomers studied its light, they weren't just measuring gases, they were reading a history written around another star, a history preserved for eons in darkness, a history that survived chaos, ejection, and endless travel to arrive, briefly, here. And then it left. No second visit, no return, just a fading trail of data and a permanent mark on science. Future generations will discover many more interstellar visitors, some larger, some stranger, some easier to study. But 3I ATLS will always be remembered as one of the first to show us that the galaxy is not distant, it is active, and it is reaching us constantly. This was not a story about fear. It was not a story about invasion. It was a story about connection. Because if a simple comet can travel between stars, then ideas, chemistry, and possibility are not confined to one place. 3I ATLS is already gone, but what it taught us remains. We are not isolated observers looking out from a lonely system. We are part of a moving galaxy, and sometimes the galaxy passes right by our door.